Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to start by picturing something in your mind right now. Just close your eyes for a second if you can.
Well, unless you're driving, right?
Oh, yeah. Please do not close your eyes if you're driving. But otherwise, I want you to visualize holding an object the exact size of the planet Jupiter.
That is a massive object to hold in your hand.
Right. Just picture this massive swirling sphere resting right there in your palm. And you're bracing your arm, preparing for the crushing, incomprehensible weight of a gas giant.
Which would be terrifying.
Exactly. The sheer gravitational pressure of a world that size, it should be enough to collapse your entire skeleton instantly.
Without a doubt.
But instead, when you actually try to lift it, you discover that this entire Jupiter-sized world weighs less than a giant ball of cotton candy.
Which just doesn't make any sense.
It totally defies all your expectations.
Yeah.
Your brain, it almost cannot compute what your hands are feeling because the physical laws you rely on every single day are suddenly screaming that this object should not exist.
It creates a complete cognitive short circuit.
Yeah.
Our brains evolved on a rocky terrestrial world,
Yeah, Earth.
Right.
Yeah.
And here, we inherently associate massive volume with massive mass. You look at a huge boulder, it possesses significant density. You don't expect it to float away.
You expect to break your toe if you kick it.
Exactly. So you look at a planet the size of Jupiter, and astrophysics dictates that it must possess tremendous gravity, driven by a deeply compressed core and layers of ultra-dense material.
Because that's what Jupiter is.
Yes, exactly. Breaking that fundamental physical expectation forces us to confront just how limited our earthbound common sense intuition actually is when we apply it to the broader mechanics of the cosmos.
Okay, let's unpack this, because leaving our common sense at the door is the absolute core of our mission today. We are traveling a long way out, right?
Very long.
Yeah, 1,110 light years away from our solar system. We are heading deep into the southern constellation of Volans, which is the Flying Fish constellation.
A great name, by the way.
It really is. And we are focusing our attention on a newly confirmed pair of planets orbiting a sun-like G-type main sequence star known as TOI 791.
And we should clarify, these aren't your standard exoplanets.
No, not at all. They belong to a highly elusive category known as superpuffs.
Superpuffs, which is such a whimsical label for a phenomenon that fundamentally challenges our models of planetary formation.
It sounds like a cereal brand.
It does. But exploring these superpuffs requires us to, completely abandon the idea that our own solar system is the standard blueprint for the universe.
We're not the main character.
Exactly. The cosmos constantly proves that it operates on extreme variables. And our goal today is to examine the specific astrophysical conditions that allow a star to forge a planet that is practically hollow.
Which is mind-blowing.
Right. And to understand how these bizarre, fluffy anomalies force us to basically rewrite the timeline of cosmic evolution.
So before we can even touch on the timeline of how a cotton candy world forms, we really have to ground ourselves in the sheer scale of the environment and the staggering physical contradiction of their existence.
We have to set the scene.
Right. Let's look at the neighborhood. TOI 791 is 11,110 light years away. For anyone who follows astronomy, you know that distance places this system well beyond our immediate stellar neighborhood.
But it's still within the Orion arm of our Milky Way.
Yeah. And what makes that specific distance interesting is, let's do the math for a second. A single light year is nearly 6 trillion miles, right? Or about 9.7 trillion kilometers.
Take or take.
So if you multiply 1,110 by 6 trillion...
You're looking at over 6.6 quadrillion miles away.
6.6 quadrillion miles. That is just a mind-boggling number. The light we are receiving from this star today, it began its journey during the European Middle Ages.
Which is incredible to think about. We're essentially looking at a system deeply embedded in the galactic disk, which means the star formed from a very specific molecular cloud with its own unique ratio of heavy elements.
And that ratio matters a lot, right?
Oh, absolutely. The metallicity of that specific region in the Orion arm is a crucial piece of the puzzle. It directly dictates the raw materials available when TOI 791 ignited.
So if a star system forms in a region depleted of heavy elements...
What astronomers call low metallicity.
Right, low metallicity. The resulting planets are going to be starved of the rocky silicates and iron needed to build dense cores.
You can't build a rocky planet if you don't have any rock.
Exactly. So we are observing a system that had to construct Jupiter-sized worlds using a radically different material budget than our own sun had.
And that budget deficit leads us directly to the density anomaly.
Which is the craziest part. We see the profile, the raw volumetric footprint of a gas giant, but the scale is a complete cosmic deception.
It's all a trick of the light, almost.
To put a massive anchor on this, our own Jupiter is up to 35 times denser than these two superpuffs.
35 times.
When we think about Jupiter, we aren't just thinking about a big cloud. We are talking about a world so massive that the pressure inside it alters the fundamental phase states of matter.
Yes, deep beneath Jupiter's cloud tops, the pressure is millions of times greater than Earth's atmosphere.
It's violent.
Very. It forces hydrogen gas to compress so violently that the electrons literally detach from their nuclei,
turning the gas into a sloshing ocean of liquid metallic hydrogen, which is just insane.
It is. And that generates a magnetic field that acts like a lethal radiation shield. Basically, Jupiter is an armored tank.
A heavily armored tank. And then you look at these two planets in Volans, and they are practically ghosts.
The contrast is staggering when you really drill down into the thermodynamics of density, because density isn't just about weight.
Weight tells you what's going on inside.
Exactly.
Yeah.
It is the ultimate indicator of a planet's internal engine. Jupiter's high density implies a massive, active core generating immense internal heat, compressing the layers above it.
So when we observe the superpuffs in the TOI 791 system, their extreme lack of density tells us what?
It tells us that this internal compression engine is either completely missing or fundamentally broken.
Which brings me to this brilliant tactile analogy from George Dransfield. She's an astronomer at the University of Oxford who worked on the analysis of these worlds.
Yes, her work on this is fascinating.
She described their density as being comparable to a, quote, nice blob of shaving foam fresh from the can.
The physics behind that analogy are actually surprisingly accurate.
Really? Like literal shaving cream?
Yeah, think about it. When you dispense shaving cream, the sudden drop in pressure allows the propellant gas trapped inside the gel to rapidly expand. It creates a matrix of microscopic bubbles.
Right, it puffs up in your hand.
Exactly. The volume increases exponentially, but the mass remains identical to the tiny squirt of gel you started with.
You press the button, the gel expands into this massive puffy cloud in your hand. It has dimension, it blocks light, but you can blow on it and it scatters.
Which is a perfect visual for these planets.
But this is where the shaving foam analogy creates a massive physical paradox for me, and I need you to resolve this.
I'll do my best.
If these planets possess a density equivalent to expanded foam, how does a structure the size of Jupiter even maintain its cohesion? I mean, a planet isn't sitting in a vacuum, right?
Well, space is a vacuum, but the environment around a star is certainly not empty.
Right. It's constantly being blasted by the solar wind of its host star. So why doesn't a planet made of literal fluff just get shredded and blown out into the interstellar medium?
What's fascinating here is that the survival of these planets hinges entirely on a delicate, almost precarious gravitational truce.
A truce?
Yes. The extreme lack of density points us toward a very specific chemical reality.
Yeah.
These planets possess what we call hydrogen-helium-dominated envelopes.
Okay, hydrogen and helium.
Right. They are the two lightest, most buoyant elements in the universe. But even though they are incredibly light, they still possess mass.
And if they have mass, they have gravity. But the gravity of a shaving foam planet must be incredibly weak.
It is very weak.
So how is it strong enough to hold on to gases that inherently want to expand and dissipate, especially when heated by a nearby star?
The mechanism keeping them intact is a concept known as the Jeans escape parameter.
Jeans escape. Okay.
Every gas molecule in a planet's atmosphere possesses kinetic energy, meaning it is constantly vibrating and bouncing around. The hotter the gas, the faster the molecules move.
That makes sense. Heat is energy.
Right. And if a molecule reaches a specific speed, the escape velocity, it overcomes the planet's gravitational pull and bleeds off into space.
So it's a race, basically, between the planet's gravitational anchor and the thermal energy injected by the star trying to boil the atmosphere away.
Precisely that. Because TOI 791 is a sun-like star, it is blasting these planets with high-energy ultraviolet radiation.
Just baking them up.
Yeah. This radiation strikes the outer layers of the hydrogen-helium envelope, heating the gas and driving up its kinetic energy. Now, the planet's gravity is incredibly weak due to its low mass, so the escape velocity is quite low.
So why hasn't it all evaporated?
The reason the entire planet hasn't vanished is that the outer envelope absorbs the brunt of this thermal assault, swelling outward dramatically rather than instantly boiling off.
Oh, wow. So it inflates like a cosmic hot air balloon to absorb the energy.
Exactly, expanding its volume to dissipate the heat, which in turn drastically lowers its overall density even further.
That thermodynamic expansion is exactly why they appear as superpuffs. The planet isn't just naturally fluffy, it is actively ballooning in response to stellar radiation.
It's a reaction to the environment. The gravitational pull from the core is just barely sufficient to tether the lower layers of the envelope, creating this fragile equilibrium.
It sounds stressful.
It is a constant agonizing tug of war between the star trying to strip the planet naked and the planet's weak gravity clinging to its expanding outer shell.
That fragile equilibrium creates such a vivid, almost haunting image of these worlds. But I think we need to bust a pervasive myth right now for everyone listening.
I know exactly where you're going with this.
Because we use terms like cotton candy, it's incredibly easy to visualize these superpuffs as giant, glowing pink carnival treats floating in the void.
Which would look cool, but is entirely wrong.
Right. If a probe were actually flying past these planets, the visual reality dictated by atmospheric physics would be entirely different. They are not pink.
Not at all. The optical properties of a hydrogen-rich envelope completely rule out any neon pink aesthetics. The visual appearance of a gas giant is dictated entirely by how its atmosphere interacts with incoming starlight.
And that's based on the chemicals in the air.
Exactly, a process largely governed by Rayleigh scattering and the presence of specific cloud condensates.
Okay, let's break that down. So if we have a deep, relatively clear atmosphere dominated by hydrogen and helium, we're likely looking at a world that scatters short-wavelength light.
Which is the blue end of the spectrum.
Right. That would give it a deep, translucent blue hue, functioning on the exact same basic optical principles that make our own sky blue on Earth.
Though likely much more profound given the sheer depth of the envelope, a pure hydrogen atmosphere would indeed scatter blue light very efficiently.
But it might not be pure hydrogen.
Right. Dransfield's research team suspects that these envelopes might not be clear at all. The thermodynamic profile of these superpuffs suggests that their upper atmospheres are likely cool enough to support massive global cloud decks.
But obviously these wouldn't be water clouds like we have on Earth, right?
Oh, no. Or even the ammonia clouds that band Jupiter.
So what kind of chemistry are we talking about for clouds on a shaving foam planet?
Depending on the specific temperature, we could be looking at clouds composed of photochemical hazes.
Like smog.
Kinda, yeah. Or even exotic condensates like salt crystals or silicate dust suspended high in the atmosphere.
Wait, really? Salt clouds?
Yeah, salt or even tiny grains of sand, essentially.
Yeah.
And if the atmosphere is choked with these high-altitude hazes, the optical effect shifts from Rayleigh scattering to Mies scattering.
Okay, Mies scattering. That's where the particles are large enough to scatter all wavelengths of visible light equally, right?
Exactly. So instead of just scattering blue, it scatters everything.
Which means, rather than a translucent blue sphere, we might be looking at a brilliant, blindingly white world.
Just a stark white orb.
Like an impossibly massive snowball suspended in the darkness, but with edges that are incredibly soft and diffuse, fading seamlessly into the vacuum of space.
The lack of a sharp limb, the distinct edge we normally see when we look at a planet, is a defining characteristic here.
Because it's so puffy.
Right. The atmosphere is so extended and so diffuse that there is no hard boundary. Just a gradual hazy transition from the intense white reflection of the cloud tops out into the blackness of the Volans constellation.
Visualizing a hazy, edgeless white giant is beautiful. But what absolutely staggers me is the technological gauntlet we had to run just to prove these soft-edged ghosts exist.
It wasn't easy.
Finding a superpuff isn't a matter of just pointing a telescope and taking a picture. It requires a relentless, multi-stage photometric and spectroscopic relay race.
A relay race is the perfect way to describe it.
Let's break down the timeline, starting with the transit detection by NASA's TESS satellite.
TESS, the Transiting Exoplanet Survey Satellite. It operates on a brilliantly simple geometric principle, but executed with terrifying precision.
It's just watching for shadows, basically.
Essentially, yes. It watches for transits, which occur when a planet's orbit carries it directly between its host star and our vantage point.
Like an eclipse.
Exactly. As the planet crosses the face of the star, it blocks a microscopic fraction of the star's light.
But wait, because these planets have such a low density, they don't have a solid silhouette. Does that diffuse, hazy edge make the transit harder for tests to detect?
That is a very good question.
I mean, if the edges are basically transparent gas, does the star's light just bleed through, muddying the data?
That is an excellent complication to highlight. The diffuse nature of the atmosphere absolutely does affect the light curve.
The light curve is the graph of the star's brightness over time.
Right. Instead of a sharp, sudden dip in starlight as a solid, rocky edge crosses the star, a superpuff can create a slightly softer, more gradual curve.
Because the light is filtering through the haze.
Exactly. The tenuous outer atmosphere begins to filter the light before the opaque main body fully blocks it. However, the core photometric dip is still governed by the sheer cross-sectional area of the planet.
And TESS can handle that.
Oh, easily. Yeah. TESS is equipped with 4 wide-field CCD cameras that are sensitive enough to measure changes in stellar brightness on the order of parts per million.
That is absurdly precise.
It really is.
So even with a soft edge, TESS measures the total drop in photons and calculates the physical diameter of the blockage. TESS runs the numbers and says, we have an object here that has the exact volumetric radius of Jupiter.
But knowing the size is only half the battle?
Right, because TESS gives us the geometry, but it is completely blind to the mass.
And geometry without mass leaves you entirely in the dark regarding density.
You can't know how heavy something is just by looking at its shadow.
Precisely. To weigh a planet 11,110 light years away, we have to shift our methodology entirely. We have to look at the gravitational influence the planet exerts on its host star.
And this is where the astronomical relay race handed the baton down to ground-based observatories.
Specifically utilizing the ASTEP telescope.
Down in Antarctica. And I have to ask, why Antarctica? That seems like an incredibly hostile place to put a delicate astronomical instrument when you could just, I don't know, build it in Hawaii or Chile.
It is hostile, but Antarctica offers a very specific observational advantage. The polar night.
Ah, of course. The sun doesn't rise.
Right. When you are trying to measure incredibly subtle gravitational interactions over long orbital periods, you need continuous, uninterrupted observation.
Because if you miss a piece of the orbit, your math is wrong.
Exactly. A telescope in Chile is blind for 12 hours a day when the sun is up. But ASTEP, positioned at the Concordia station on the Antarctic Plateau, can stare at the Volans constellation continuously for months at a time during the Antarctic winter.
Without the diurnal cycle breaking the data stream?
It just stares into the dark, gathering data.
And that continuous data stream is hunting for radial velocity shifts, right? Walk us through the mechanics of how we use that to weigh a planet. Because we know gravity is a two-way street.
It is.
The star pulls the planet into orbit, but the planet's mass also tugs back on the star, causing the star to wobble slightly around the system's center of mass.
The radial velocity method measures that precise stellar wobble by analyzing the star's light through a spectrograph.
So we're looking at the light again, but differently.
Right. As the unseen planet's gravity pulls the star slightly toward Earth, the light waves emitted by the star are compressed. This shifts them slightly toward the blue end of the electromagnetic spectrum.
And then it swings around.
As the planet orbits to the other side and pulls the star away from us, the light waves stretch out, shifting toward the red end.
The Doppler effect. Exactly like the pitch of an ambulance siren rising as it approaches you and falling as it speeds away. Except here, we are measuring the changing pitch of starlight.
That's a perfect analogy.
But wait, if these superpuffs have the mass of just a few Earths spread out over the massive volume of Jupiter, their gravitational tug must be microscopic?
It is incredibly faint.
Because the star TOI 791 is massive. Getting a shaving foam planet to make it wobble must be like, a mosquito trying to drag a bowling ball.
The signal-to-noise ratio is punishing, truly punishing. We are talking about detecting a star moving at a velocity of perhaps a few meters per second from a distance of over 1,000 light years away.
That's walking speed. We're detecting a star walking.
Yes. Ground-based spectrographs have to isolate that tiny rhythmic Doppler shift from the chaotic, turbulent boiling of the star's own surface plasma. It's an immense data challenge.
But they did it.
They did. And when the ASTEP data was finally analyzed, the math revealed the paradox. TESS provided a massive volume. ASTEP provided an agonizingly tiny mass.
You divide the tiny mass by the massive volume, and the resulting density equation spits out a number that makes planetary scientists question their own instruments.
Because it just feels wrong.
Here's where it gets really interesting. We've solved the density equation, but we are still blind to the actual chemical inventory of that extended atmosphere. We've hypothesized the hydrogen-helium envelope based on the mass, and we've guessed at the photochemistry of the clouds.
But guessing isn't science. We need definitive proof.
And that requires a tool that TESS and ASTEP cannot provide.
The final leg of this observational marathon requires transmission spectroscopy, which is arguably the most complex technique in modern astrophysics.
And to execute it with the precision required for a super puff,
we have to utilize NASA's James Webb Space Telescope.
So if we can't physically send a probe to scoop up the gas, Webb has to rely on the starlight passing through the atmosphere during a transit. It's almost like looking for the molecular shadows cast by the chemicals.
That's exactly what it is.
How does Webb separate those shadows from the blinding glare of the star itself?
It operates on the principles of quantum mechanics. When the starlight from TOI 791 filters through the wispy outer edges of the superpuff's atmosphere, the photons interact with the gas molecule.
They bump into each other.
Right. But molecules don't just absorb light randomly. The chemical bonds in a molecule of water or methane or carbon dioxide will only absorb photons that carry a very specific, quantized amount of energy.
And because the energy of a photon dictates its wavelength or its color, a specific molecule will only ever absorb a specific color of light.
Correct. So as the starlight passes through the atmosphere, the specific molecules present in the gas will absorb their corresponding colors, essentially removing them from the light beam.
So the light that reaches us is missing pieces.
Yes. When that filtered light finally hits the spectrographs on the Webb telescope, we don't see a continuous rainbow. We see a spectrum crossed by dark, missing bands.
The missing colors act like a chemical barcode.
Exactly like a barcode.
If we see a missing band at, say, 1.4 microns, we know the starlight bumped into water vapor. If there's a gap at 3.3 microns, we know it hit methane.
Webb is essentially reading the absorption barcode from across the galaxy.
Which is just staggering when you think about it.
And this barcode is going to do far more than just confirm the presence of hydrogen. The specific ratios of carbon to oxygen, or the isotopic signatures trapped in that gas, they act as a forensic time machine.
A time machine? How so?
Because the chemical inventory of the atmosphere today contains the fossilized evidence of exactly where and how this planet formed billions of years ago.
Which provides the perfect narrative bridge to the ultimate question. Webb's barcode will tell us the what, but we really need to understand the how.
Right, the origin story.
How does a star system cook up something so fundamentally weird, and why are they so incredibly scarce?
They are very, very rare.
If we look at the exoplanet census, we have confirmed roughly 6,300 worlds, give or take. We have massive hot Jupiters skimming the surface of their stars. We have rocky super-Earths. We have rogue planets drifting in the dark.
A huge variety of planets.
But out of those 6,300, fewer than 40 are classified as superpuffs. That's a statistical anomaly so extreme it demands an explanation.
Their extreme rarity is the loudest clue we have about their origin. If superpuffs were a standard byproduct of stellar evolution, our surveys would be flooded with them.
Because they're huge, they cast big shadows.
Right, their massive size makes them incredibly easy for telescopes like TESS to spot. The fact that we have found so few tells us that the astrophysical recipe for a superpuff requires a highly specific, transient, and delicate set of initial conditions.
Conditions within the protoplanetary disk.
Exactly.
Let's rewind the clock to that stellar nursery. A star is born, and it is surrounded by this chaotic, swirling accretion disk of gas and dust.
Standard planetary formation.
Right, the core accretion model. It dictates that dust grains collide, stick together, form pebbles, then planetesimals, and eventually build a solid rocky core.
Building a planet from the ground up.
Once that core hits a critical mass, maybe 10 times the mass of Earth, its gravity triggers runaway gas accretion, vacuuming up the surrounding hydrogen to become a dense gas giant.
That's how Jupiter formed.
But for a superpuff to form, that standard assembly line has to completely derail.
And the derailment occurs in the ratio of solid building materials to available gas.
So, too much gas, not enough rock.
More or less.
Yeah.
We hypothesize that superpuffs form in highly specialized zones of the disk. often further out beyond what we call the snow line.
Where volatile compounds like water and ammonia freeze into solid grains.
Right. However, in the specific case of a superpuff, the disk in that region is somehow starved of solid dust and pebbles, but remains heavily saturated with cold hydrogen gas.
Okay, it's like trying to build a snowman in a dense, freezing fog bank.
Okay, I like this. Let's hear it.
If you roll a snowball down a snowy hill, it packs on dense, heavy snow and ice, growing into a solid, heavy mass. That's a standard gas giant.
Right, gathering solid material.
But if you roll a small snowball through a freezing fog, it can't pack on solid mass. It just gathers a massive, uncompressed, crystalline halo of frost. The volume expands dramatically, but the weight barely changes.
That is a phenomenal analogy for the fluid dynamics at play here.
Thanks. It just makes sense in my head that way.
The small planetary core forms, but because the local environment is dust poor, the core never reaches the critical mass required to trigger violent, compacting, runaway accretion.
It never gets heavy enough to crush the gas.
Exactly. Instead, its weak gravity slowly gathers the surrounding frigid, low-density gas. Because the gas is cold, it lacks the thermal energy to resist the weak gravitational pull.
So it just piles up.
Right, allowing the planet to accumulate a massive atmosphere without compressing it.
It slowly wraps itself in this massive extended halo of freezing fog. But that begs a massive evolutionary question for me, because the universe is dynamic.
Very dynamic. Things don't stay still.
The protoplanetary disk eventually dissipates, the star fully ignites, and suddenly this delicate, freezing fog bank of a planet is exposed to the searing reality of stellar radiation.
The star wakes up and starts cooking everything.
Right. And you mentioned that these planets shed their material over time. This makes me seriously question our entire classification system.
How so?
Are we actually looking at a distinct, permanent class of planets? Or is a superpuff just a fleeting, awkward teenage phase in a planet's evolution?
A cosmic phase, basically.
Yeah. If we observe TOI 791 a billion years from now, will that fluffy blue exterior have completely boiled away, leaving behind a naked, barren core?
You are tapping into one of the most contentious debates in planetary science right now.
Really?
Well, absolutely. The theory of atmospheric photoevaporation strongly supports your suspicion. The sheer volume of a superpuff makes it incredibly vulnerable.
Because it's so spread out.
Yes. The stellar ultraviolet X-ray radiation that we call the XUV flux, it acts like a cosmic blowtorch.
Heating that upper envelope until the kinetic energy of the molecules violently shatters the gene's escape parameter we talked about earlier.
Exactly. We're very likely observing a transient phenomenon. Hydrodynamic escape takes over.
Hydrodynamic escape.
That's where the upper atmosphere heats up and expands so rapidly that it creates an outward wind. It physically drags heavier molecules along with the escaping hydrogen.
Like a rip current in the sky.
Yes. Over hundreds of millions of years, the planet bleeds its mass into space, trailing a comet-like tail of escaping gas.
So the shading foam is actively melting in the heat of the star.
Yes. And if TOI 791's planets are migrating inward, getting closer to the star, that evaporation will accelerate exponentially.
It'll just melt faster.
Over a deep geological time, a Jupiter-sized superpuff will likely be eroded down to a mini Neptune. And eventually, the stellar wind will strip the envelope entirely, leaving behind a dense terrestrial super-Earth.
Just the pit at the peach.
Exactly. So classifying them as a permanent planetary type might actually be a mistake. We are likely just catching a brief snapshot of a violent cosmic diet.
And if they're just a temporary phase, that raises the ultimate why for me.
Why study them?
Yeah. Why do we dedicate decade-long satellite missions, brave the polar night of Antarctica, and aim a $10 billion quantum space telescope just to look at an awkward teenage planet that won't even exist in its current form a billion years from now?
If we connect this to the bigger picture, the answer lies in the philosophical foundation of the scientific method itself. Dransfield expressed it perfectly. By studying exotic systems and rare anomalies, we add the missing pieces to the grand puzzle of planetary formation.
It's the anomalies that stress test our models. If a theory of physics only works for the planets in our backyard, it's not a universal law.
No, it's just a localized coincidence. If we restrict our observations to the norm, our understanding stagnates.
We get comfortable.
Exactly. Before we discovered exoplanets, we assumed our solar system was the rigid template for the galaxy. Rocky planets close to the star, gas giants far away.
Because that's all we knew.
But then we looked out into the Orion Arm and found hot Jupiters practically touching their host stars. We found rogue planets with no stars at all,
Just drifting.
and we found superpuffs, hollow ghosts made of uncompressed gas. Every time we encounter an anomaly that breaks our mathematical models, it forces us to rebuild those models with greater complexity and accuracy.
We have to write better math.
Yes. Superpuffs are the extreme boundary condition that tests our understanding of fluid dynamics, orbital mechanics, and quantum spectroscopy.
So what does this all mean for you listening right now? It means that understanding the bizarre worlds orbiting TOI 791 isn't just an exercise in cataloging weird cosmic trivia.
It's far more important than that.
It is a fundamental stress test of reality. We journeyed thousands of light years today, looking back through centuries of starlight, to find planets the massive size of Jupiter, but with the paradoxical density of a fresh squirt of shaving foam.
A cosmic paradox.
We use the physics of light scattering to paint a vivid picture of hazy, edgeless white and blue skies. And we unpacked the agonizing gravitational tug-of-war that keeps them from blowing away in the solar wind.
It's a delicate balance.
We tracked the incredible human ingenuity required to weigh a ghost using the Doppler shift of a wobbling star. And most importantly, we learned how their rare cold birth in the dust-starved regions of a stellar nursery helped scientists piece together the brutal mechanics of cosmic evolution.
We're watching it happen.
By observing them now, before the stellar winds strip them down to barren rock, we are quite literally watching the relentless engine of the universe actively sculpting a world.
It is a profound realization that the cosmos is a dynamic, evolving laboratory. And it leaves me with one final provocative thought for you to carry with you today.
Oh, I'm ready. Let's hear it.
We just explored how a highly specific imbalance of cold gas and low gravity can forge a massive planet that perfectly mimics the density of shaving foam. It is an extreme physical state that challenged our core assumptions of what a planet could be.
Right. It broke the rules.
So if the universe is capable of engineering something that bizarre, what other seemingly impossible extreme physical states are currently orbiting the billions of stars we haven't analyzed yet?
Oh, wow.
Could there be entire worlds out there constructed from exotic states of matter, like superionic water ice that is simultaneously solid and liquid? Or matter compressed so strangely it literally defies our current periodic table? What other impossible things are just waiting for a telescope to catch their shadow?
It makes you look up at the night sky and realize that the dark, silent spaces between the stars are hiding secrets that our physics textbooks haven't even dreamed up yet. Thank you for joining the conversation today, for opening your mind to the impossible, and for matching our curiosity step for step. We will catch you on the next one.